Okay, so welcome back. So today I'm going to review what we have discussed previously about entanglement property, such as concurrence, negativity, entanglement entropy, and related entanglement distillation, dilution process. Then I'm going to continue this week's topic. So any questions? Okay, so let me just review concurrence. So it's only for two-qubit. And it defined through a time reversal of a wave function, and concurrence is basically asking how close they are. So
why you need the sigma y to reverse the time?
if you are spin a half particle, then you need to if you reverse the time, it would take the spin up to spin down, and vice versa. So you need a sigma y.
But for y, there is a minus sign.
There's a what?
I sigma y, I think is minus 1, 1.
Yeah, so there's a convention of the minus sign. It's basically its rotation around the y. If you remember in your quantum mechanics, I think it's like this. This time reversal. It's basically a rotation in y-axis by pi over 2 angle and then complex conjugation. It's a convention, so it's chosen to be the y rotation. You could choose to be other axis rotation. That would be fine. In probably modern condensed matter, you have seen time reversal in different ways. But we're going to use probably the most basic way that people have defined is this rotation around y and complex conjugation. Okay, you can maybe refer to, let's say, quantum mechanics by Sakura. Okay, but this is not that so important. I just want to give a meaning of the concurrence. But if you really start from a math point of view, what we have seen is that this is nothing but 2 times a d minus bc. Okay, basically that's all you need, and this is a quantity that quantify entanglement for 2-qubit system. Okay, this is for pure state. For mixed state, we generalize this. So mixed state will be written as a density matrix. We generalize so that we define a rho tilde, defined to be applying the time reversal. So I'm going to ignore these the I because if you have a density matrix, then if you turn this to a density matrix, this will be simply the phase or the -1 square cancel out, but you are just rewriting that. Okay. So mixed state is more complicated. You have to form this density matrix, and then you take the product and find eigenvalue lambda 1, lambda 2, lambda 3, lambda 4, because they are four. It's 4x4 matrix. So concurrence basically is taking the largest square root minus the rest. Okay. If it's not negative, then that will be the value, but if it's negative, then it's defined to be 0. This is called Wootters formula. So, but it's not the detail. I mean, won't be able to prove, of course, because this take a lot of effort for Wootters to prove this in his proof for the exact formula for entanglement formation. This is called Wootters formula. But at least you see the structure and related time reversal. Okay, but this may be complicated, but there is this formula. Exists a formula. So, and you have probably already seen my mathematical notebook that evaluate that. Okay, so this is concurrence. Negativity, this is related to positive partial transpose. Maybe I should say that's the opposite of the PPT. Just to take an example, if you have a pure entangled state like this, then you write as a density matrix. In the basis 0, 0, 0, 1, 1, 0, 1, 1. This will be 1 at the four corner. Partial transpose basically just taking the transpose of each blocks. Partial transpose. Okay, so you get 1 and then 1 at the middle. So basically a sigma X matrix in the middle. Okay. So this has eigenvalue 3 of plus 1/2 and 1 negative 1/2. So this means that it's entangled because you have a negative eigenvalue after partial transpose. So negativity is basically defined as 2 times the negative parts and taking the absolute value. So in this case, this is 1 for the Bell state. This factor of 2 is just a definition so that negative is 1 for the Bell states. Okay, so that's the one way to check whether a state is entangled or not. For pure states, checking whether it's entangled is easy. And usually we also define something called entanglement entropy. So this will be for a two-qubit, or this in general for arbitrary number of qubit pure states. So you would, but you would separate into 2 parts. So by partition, say A and B, and you have to trace out B. And we talk about how you trace over Bpart. And so the entanglement entropy is the polynomial entropy of this density matrix. Okay, so that's row. Trace row A, log row A. Okay, and you can just work in eigenvalues. For the eigenvalue, that will be this. Or in terms of Schmidt coefficient, this will be sigma k squared, sigma k log sigma k squared. So let me just write. You could do a Schmidt decomposition. And this sigma k are the Schmidt coefficient. Okay, so, and we also talk about entanglement distillation. So distillation basically take many copy of not so entangled states. You have many of them, and you want to concentrate to a small number of Bell pair. Okay, so this would be a Bell pair, half. Each would have half of the Bell pair. Okay, so if you start with N and distill only K, this entanglement of distillation is defined as K over N. The other, or the reverse process called entanglement dilution, which is the other way around. So imagine you have K copies of Bell states, and you want to generate more of the psi. So this will be half, meaning that this is entangled with the other part. Okay, suppose you can distill dilute into n of them, so this entanglement dilution, or sometimes also called entanglement cost, is the ratio k over n. Okay. Any question on any of these content? Okay, so if not, I'm going to continue. So this entanglement cost is how much it's related to this entanglement dilution, how much you need to use the Bell state in order to create the psi. This generates to any mixed state, but the question is, this is very difficult to, so entanglement cost or entanglement dilution. So it's just the same object but different names. It's k over n, and actually it's in the limit of you have supplied many copies of k and distill many copies of n. This is very impossible, almost impossible to calculate. Calculate. So one way to do that is this is for mixed state, very difficult. One way to do that is maybe let's just take some average. If I can decompose a mixed state into mixture of pure state, so we learn this notion that any mixed state can be decomposed into pure states, mixture of pure states, and the decomposition is not unique in general. So I want to define something called entanglement formation, which is average over the component of entanglement cost. So the average is the probability of getting pi, multiply the cost to create that pi, psi I, the psi I are from this process. And you sum over that, and you minimize because you want to find the minimum cost. Okay, yeah, so one thing I forgot to mention for pure state, this is related to entanglement entropy, okay? So the way to define minimization is you don't want to define something that could have non-zero entanglement formation and is yet it a not entangled state, right? So we learned previously that so for example, a pure so as a separable state could be written as this, right? But sometimes you could also take, for example, you might be able to take a decomposition which is not really in terms of this. For example, if you take a mixture of this, it's a mixture of two Bell states. So let me just remind you what these are. If you take a mixture of these, each is highly entangled. It's the maximum entangled state you can have for 2 qubits. But after doing the mixture, you find out this is also equivalent to this, right? So you want to define the entanglement to be the minimum over all possible decomposition. In this case, the average entanglement will be 0 because each component is 0. But if you use this to calculate the average entanglement, then it will be 1. But you don't want to define an intrinsic separable state to have non-zero entanglement. Okay. So that's why you have minimization. And I also show you there's an analytic formula for that Wootters calculate the entanglement formation. It's actually related to concurrence. So entanglement formation is actually a function of the concurrence that I just showed you earlier. Concurrence, yeah. So, and remember previously we have these, sorry, go back. We have this spin model, 2-qubit spin model. And there's if you have a thermal bath, then you can write a 2-qubit state at some temperature as a thermal state like this. And we've seen this before, and you can use that Wootters formula. You can calculate the entanglement formation. So last time I showed the entanglement in terms of concurrence, but they are equivalent up to a function. Okay, one-to-one function. And you see that like this system, simple system, has entanglement until a temperature around 3 point something. Okay. Yeah, so this is Wootters formula. So let me just write that. Let me just remind you. So I already showed you the concurrence is this for mixed states. And these lambdas are eigenvalues of the product of these two. This density matrix and this time reversal one. And as I said, this is entanglement formation is a function of concurrence, and that's the exact expression here. Okay. Okay, and yeah, in terms of concurrence, it's similar. Of course, it has to be 0 when the entanglement formation is 0. They are just 1-to-1 corresponding to each other. So any question on this? You don't need to remember Wootters formula. If you can plug in to the mathematical formula to calculate, and that's already good enough.
What is EF and EC?
So EF is defined as entanglement formation. EC, okay, I might have used EC or EF.
EC is in the
EC is entanglement cost.
Yeah.
Entanglement cost. For pure states, really, they are really the same, just entanglement entropy. Okay. Yeah, so maybe let me go back with slide. Yeah, so I've written here, but just show you the picture. Right, this is distillation. So it's called E subscript D. Okay, but as I show you the intuitive that it can be this it can be calculated using this entanglement entropy. Okay, so and distillation, I gave you one example last time. Entanglement cost is the reverse. It's how much entanglement you need to use to create a state psi with many copies. Okay, so this EC. There are many names, but they're mostly for pure state. They're the same, but for mixed state, it's very difficult to calculate. So I think the Wootters formula is sort of quite an achievement for proving that. Initially, it was a conjecture, and then they checked it seemed to be correct, and then there was a paper on this proving that. Yeah. Okay. So we've seen a few entanglement measures. So people sort of think about how do I define good entanglement measures, and there's some criteria. So of course, if a state is not entangled, this entanglement measure E, we just call it E, has to give you 0, right? But in general, it should be non-negative. Okay, that's trivial. More importantly, we see that entanglement cannot be created using local operation. So there's a requirement if you only have local unitary transformation. Okay, this is local unitary. It's even more restricted. So local unitary basically just means this row goes to this. And we know local unitary just basis transformation. Local basis transformation, so it should not change entanglement. Okay, so that's should be obvious, because if you think in terms of Schmidt decomposition for pure state, that's the case. Third, if you have local operations, so that include measurement, right? So remember I was using the two pairs of two-qubit state to illustrate the entanglement distillation. There I need to use some measurement, and with the outcome that I have to inform the other party to do some unitary. Okay, so if you have local operation and classical communication, so under that you may produce a state rho k, but it may appear with some probability pk. So in this process, the entanglement should not increase, right? And there are few, at least two ways to write that as a constraint. Okay, this is just a name. The first is called strong monotone. is that, okay, I have many products. If I take average of all these products, that average entanglement should not be bigger than the initial, right? So average of entanglement over different outcome should be less than initial entanglement. Okay. The second one is slightly weaker. So instead of averaging the entanglement of over different product, I just first average over product, over a different product, or a different outcome to get a row, sort of average row. That's this. And then averaging row, the entanglement of that should also be less than the initial entanglement. Okay. There's also a slightly more subtle condition, meaning that entanglement cannot increase under discarding information. This meaning the thing that I did here, averaging over the states, averaging over different outcome for the density matrix, that is a way of discarding information, right? So if you discard information, that should be smaller than you have the information of which outcome. Okay, so that's why the second condition is sort of weaker. Okay, but I just want to list all these conditions that people have proposed, and to say that, okay, if you want to write down some entanglement measure, you should satisfy most of these conditions. Okay, and these conditions sort of intuitive in terms of the fact that entanglement should not increase if you only have local operation and classical commutation. Okay. Any question?
Sorry, you might have already covered this, but like,
Can you speak louder?
yeah, you might have already talked about it, but like a few slides before it's the last section.
It's hard to hear your voice.
Yeah, my mic is kind of broken. Can you hear me now?
Yeah, barely.
Yeah, it's okay.
Okay, can you?
Can
Yeah,
I
continue. Go on.
Yeah, you might have already talked about this, but I'm still a bit confused about the EF formula, the formula of
Okay.
EF before.
Okay,
Like,
so EF, I'm just
like,
mentioning this. So if you don't
like,
understand that, it's fine, but basically it's an average, it's defined. This is usually called convex
is this a definition?
hull. It's a definition.
Okay.
This is
And
called convex hull construction. So if you have a quantity that defined for pure state, in order to extend to mixed state, what you do is you decompose to mixture of pure states. And since you have definition on the pure state, you can use that definition on pure state. So this should be EC because we have not defined EF yet. Okay, but
so this
because they are
relation,
all the same, yeah,
so EC and EF agrees on pure state. And do you
yeah.
use
So
this
yeah,
to deduce the Wootters formula, or
to define the mixed state, and then from the mixed state, you have this definition. It also looks very complicated, difficult to calculate because you have to minimize over all possible decomposition.
okay.
But it was really a sort of, I don't know, a really success when Wootters proved this formula, right?
Okay, thanks.
Okay, but now it's a formula, so you can just use that to quantify entanglement. Okay. Okay. So yeah, so the entanglement formation is about average, and the idea of entanglement distillation, entanglement cost, or in entanglement dilution, they require many copies and usually define in infinite copies. For pure state, these are the same in the sense that the two processes are reversible. So meaning that I could have, for example, phi plus, if I have k copies, I can convert into psi with n copy, and in a limit that these goes to infinity, the arrow can go backward. Okay, so it's reversible. That's what I mean. Okay, but we want to also consider a scenario if you only have a single copy. Let's say Alice and Bob shares a single copy, and we want to ask the question, can this be converted to another state phi using only local operation and classical communication? So for example, if I have these states, this is phi plus, it is the highest entanglement of all two-qubit, but we also seen other two-qubit states, which is not necessarily the highest entangle. So suppose somehow I want to use maybe I need a less entangled state for some other task, but can I get this? Can I get this? But I want to do it deterministically. But I can only ask Alice and Bob to perform operation on their local qubit. They cannot do global unitary. If you can do global unitary, you can rotate, right? But suppose they are very far away, and could you achieve this? And how do I know the process can be achieved or not? Okay, maybe let me ask, who think this is possible? I can get from Bell state to this less entangled state. Because if we want to think the Bell state is a entanglement resource, highly entangled, it should be natural to think that I can do this process. But I want to do it deterministically. So who think this is not possible? Maybe use raise hand. And who think this is possible? Or maybe not possible using thumbs down and possible using thumb up. Okay, I see at least one thumbs up. Okay, so indeed this is possible. So there is a criteria that, so that's the, okay, let me first show the picture. This is what I want. I want to ask more generally. I have a state psi and I want to go to phi. Is this possible? Okay, that's the question, general question. And there is a criteria. It used something called majorization. And Nielsen invented this criteria. And majorization was known in mathematics. So, but let me basically illustrate. So here I have a phi plus with a Schmidt coefficient, 1/√2. So there's the square of sigma k, Schmidt coefficient, is 1/2 and 1/2, right? And this one here is cosine square, sine square. Okay. I want to assume that the cosine square is bigger than sine square. If not, I would just change the other way around, okay? So majorization says, if I take the largest one and compare with the largest one from the right-hand side, this holds, and I also want to take the largest one and add the lower one. If this holds, this is called majorized. The first set is majorized by the second set. Okay, there's a symbol that says majorized by. Okay, so Nielsen basically said that if this is the case, then the process is possible. Okay, so this is the definition of majorization. So you have the square of Schmidt coefficient. You want to order so that the first one is largest, and then you order that in a decreasing order. So you have two set of number. You compare the largest one from each set. If the first one is, we just say if this x1 is smaller than y1, and then you add the next higher one, x2, the sum of this is still less than sum of y1 and y2, and it goes y3, so x3 and y3, etc. If this condition holds, then that is defined to be x. This set of number x is majorized by y, and he showed that if that's the case, then this transformation is possible with probability 1. Okay, and this condition is if and only if. Okay, so this condition is sometimes labeled like this. So lambda is the set of square of Schmidt coefficient. Of Schmidt coefficient. Basically sigma k squared. Okay. And just as a remark, if this does not satisfy, you can still do transformation with some probability, and that probability is related to this, but this is not that important. Just want to mention as a remark that it doesn't say that it's impossible. It says this condition is just to test whether this is with probability 1. Okay, so for example, you look at these two quantum states, 3 levels, right? And the coefficient square is, if I order in a decreasing order, this is this, and the other one is that. Okay, so first 1/2 is smaller than that. 3/5, but if I add 1/2 and add, so let me maybe use numerical number. So 0.5 is less than 0.6, so in 0.5 add 0.4, is it still less than 0.6 plus 0.2? It's not, right? So they have no relation in the majorization. So that means I cannot transform with certainty from psi to phi nor backward. Okay. So this is a way to check the transformation can be achieved with probability 1. Okay. Okay. So but they can be done with some non-deterministic way, but that's related to this. So, but let me not go into that. But I want to come back to the original question. So I have a failed state, and I have a state which is not so entangled, and I change the coefficient to square root p and 1 minus p, square root of 1 minus p, because they have to add up to 1. Assume p is greater than 1/2, so I know this is less than p. 1/2 plus 1/2 is less than, in this case, it's equal p plus 1 minus p. So it's satisfied. So this means I can deterministically transform psi plus, phi plus to psi, right? And how do I do this? Because I said I can do this deterministically, but how do I do that? So you need to use quantum operation. Remember we discussed this in the noise channel, right? So noise channel, let me just remind you. So we have some noise channel, okay? And we have general quantum operation, and they satisfy a condition like that. But we can do this on purpose, right? So we can create such quantum operation. So that means this can in principle be created. In our discussion of noise channel is that we add environment, and then the system environment, there is a global unitary, and when you trace out the environment, that give rise to such a noise channel, and they satisfy this. But so if we do it on purpose, we would use some ancilla to achieve such quantum operation, okay? But let me go to the deterministic transformation. So she can only, so suppose this is Alice, she can only apply M1 and M2 probabilistically, but she knows what is applied, okay? So because this is related to, you apply a joint unitary on the qubit you want, and also the added ancilla, which in the noise case is the environment. You do a global operation. When you trace out, in this case, Alice can measure the ancilla and to know what outcome you get. Suppose you get the M1 apply. So after that, you know it's successful. That means the effect is you put a square root p in front of 0 on Alice's part. You put a square root 1 minus p on the state 1, right? So that means that it is successfully transformed. And basically the overall 1 over square root square is the probability that happens. This case happens, okay? In order for all the event to be conserved, to conserve the probability, there is the other half that would be this M2, right? So when you apply the M2, the state is sort of the slightly different. It's square root 1 minus p 0 0 plus square root p times state 1 1, which is not what we want, right? But Alice can tell Bob that we both perform a operation x1, x2. So we both perform the x operation. So we can basically flip this to the correct state. So that is why this can be done deterministically. Okay. So if you don't remember Nielsen's exact criteria, then at least you should remember this example. Okay. Yeah. So just as a remark, so how do we apply this? Maybe I have an ancilla and I apply a unitary And if ancilla is 0, that's my M1, okay, acting on psi. And I want to design, if the ancilla, the measurement is 1, I apply 2. Or maybe let me just change this to 1 and change the ancilla to 2. So that has the correspondent of the operation. So this, what I'm saying here is you can design a U so that M1, M2 can be realized. Okay, any question? I think this is a very important example. Okay. Okay, looks like that you all understand this. So let me move to the next topic. So we know that some transformation cannot be successfully implemented using Nielsen's criteria. But it's surprising that if you can borrow some other entangled state, you might be able to achieve that. So this is called entanglement catalysis. This is what Nielsen's picture, right? If I check the criteria, if the majorization is not hold, then I cannot transform this using local operation, this local quantum operation, classical communication. But it is possible that even this is not allowed. If I have another entangled state, phi, jointly, the joint psi 1 and phi, if it happened to be majorized in this way, then this is possible, okay? So let me give you an example. So if I have psi 1 and psi 2, you can easily check that the two set is not related by majorization, right? You can just check, okay, if you want to, if they were to, the first set were to majorize by the second, so 0.4 less than 0.5, by adding these become 0.8, but it's greater than 0.75, so this majorization does not hold. Using Nielsen's criteria means that the transformation cannot be done with probability 1. However, if Alice and Bob have another entangled state, which is of this 0.6.4 number there, the combined system does have the majorization relation, right? So you can compare this is less than that, less than, if you add this, 0.48 still less than 0.5, and you continue to add, and you check whether the majorization is satisfied, and indeed, this is the case. So this using Nielsen's criteria means that this transformation is allowed, right? And you see that this means that this state, phi stay the same. So it's like chemistry. You have some material used as a catalysis, and with its existence, and how this help the transformation from psi 1 to psi 2. Okay, so that's somehow very interesting. Any question on this?
And the catalysis is not changed as in chemistry?
Yeah,
like,
just like chemistry. Yeah, so you can basically return this, right? Suppose you borrow this from someone, borrow that, you can basically return.
I see. Thank you.
Okay. Okay, so I want to comment on bipartite versus multipartite. So we've seen concurrence, right? And also seen the entanglement entropy. We just write entanglement entropy is with a system, subsystem, and the rest. So basically it's A and B. But there are also many party states like maybe the GZ state that you have seen. So I'm going to introduce two measures because in this context, how do we quantify the entanglement? So there are two. One is proposed by Vitro some time ago, and the other is the one that I helped to develop. So the example of multi-partite entangled state, so the GZ state, so we saw this in the violation classical realistic theory. I hope you remember that. But if not, let me just remind you. So they satisfy these sort of stabilizer condition, except that this is minus sign, right? So this means that if you want to attribute using classical theory that these GZ state already possess some property x1, x2, y1, y2, etc., and they need to satisfy this relation, right? According to this rule, which the product of x should be 1 and y1, y2, y3 should be minus 1, etc. If you multiply these four equations, you get actually a contradiction, 1 equal to minus 1. But in quantum mechanics, there is no contradiction, okay? And this means that you have a sharp distinction in checking whether classical theory is correct or quantum theory is correct. And of course, in this case, there was an experiment that verified quantum mechanics. Okay. And I want to also mention there are, with many particles, you have many ways to write down entangled states. This is one called W state. So it sort of have 0, 0, 1, 0, 1, 0, 1, 0, 1, sort of cyclic arrangement of these qubit states. This state was shown that it cannot be transformed into GZ state. It's inequivalent. So it's for a single part, for a single copy, W cannot be transformed into GZ state. And in the multipartite case, there are more, if you consider for a qubit, there are more inequivalent classes. And and more interesting, this transformation cannot even done probabilistically, not even probabilistically. So the entanglement in the multipartite case is much richer, and I think there's still a lot of new result coming out. So, but I won't be able to survey all these results. So just give you one perspective. How do we quantify the entanglement of these states? Okay. So there's one way to characterize that is using a picture like that. So suppose you have a state rho, you want to characterize its entanglement. So the idea is you compare to the set of unentangled state. And if you can define some distance, you want to find the minimal distance from rho to the set of unentangled state. That distance give you the quantification of the entanglement for this state. Okay. And it happens that in this particular proposal is using the so-called relative entropy. So relative entropy, remember we have entropy. Entropy is trace rho log rho. But relative entropy is sort of involving two states. It's trace rho log rho minus trace rho log sigma. If you want, you could also write symbolically as rho log sigma divided by rho divided by sigma. Okay. But this definition is nice, very intuitive, but it's very difficult to calculate. So for G as Z state, we know, so relative entropy is 1. And the closest state to that G as Z state is sort of 1/2 0 0. This is what I wrote down. Okay, this state is the closest to G as Z. Okay, I'm missing 1 0. 3-qubit state.
Quick question. How do you actively find such state?
Very difficult.
Okay.
In general.
Okay.
Yeah, but for this simple state, there's some simplification you can do. Okay, but in general, it's very difficult, even for pure state. For W state, it was not even known analytically what the number is. Okay, so W state, this W state. This is a mathematically well-defined question. Right? Numerically, one can search. Yeah.
Yeah.
Okay.
What about we just do the search numerically in the parameter space? That's only 64 parameter.
I think the difficulty is you also need to have a way to parameterize the space of unentangled state. Yeah, so that because in order to search, you need to search within this, right? You search point here and see what's the distance. Yeah. I schematically draw there's a boundary, but it's the real geometry is not known. Okay, we only know it's a convex set. Okay, so that's very difficult. I mean, I can not like naively write that, but for general n-qubit, then this is also very large space. Okay. Yeah. So, but I'm going to give you something has a more like easy way to calculate. This is what we call geometric measure. But I will focus on pure state. And the idea is that if I want to quantify this entangled state, I compare with really separable state, but product pure state. Okay, so it's very similar to the previous picture, but only consider the pure state. And in this way, it's easy to do the search. So I want to maximize the overlap, or if I want to minimize the distance, this is equivalent to maximize the overlap. Okay, so what it determines, I mean, the overlap determines the entanglement, right? If the overlap is 1, meaning it's on top of each other, that means psi is in the set of separable state, that means it's not entangled. But if there is some angle between them, that means it's entangled. So the larger the angle, the larger the entanglement. So that's the picture. Okay, this is a geometric picture, but defined in terms of this. So this is the state you want to characterize, and this is when I write psi, S meaning separable product state. So they are of this form here. Okay. Okay. Yeah. So yeah, this is just in terms of numbers. In terms of formula, you just arbitrary state. You really write in terms of basis, and there are coefficients, general coefficient, but we want to compare this state to product state of this form and to really maximize their overlap. Okay, so basically these are just words in terms of the picture that I show you. Okay, but you could also discuss in terms of different partition. So for example, if you may want to study the entanglement between 1 to 4, and then by to 8, and you can maybe define your separable state to be just product of the two groups, this and that. So these 4 particles can be entangled in this definition. It can be entangled among themselves, but not entangled across the group. Then you can use this to study bipartite entanglement. Okay. You could also study maybe those 3 party. You can group these as product states, and you can study different way of partitioning. Okay. But I want to just focus on the finest partition. So meaning that you take every state, every individual spin, and you consider the product of them. And this way we are studying the global entanglement of the system. Okay. Yeah, so the following is not that important because it's just detailed definition of the entanglement. So we use this 1 minus the n cosine square, or we take the log. Because this is smaller than 1, I need to put a minus sign, so that is positive number. And so the advantage of the second definition is that I can consider also large particle n. I can consider sort of entanglement per particle. Okay, and we'll see that this definition give a lower bound on the relative entropy of entanglement, ER. Let me just write ER. Okay, I won't prove that, but I just want to mention this give a lower bound on that. So meaning that this, but as I am going to show you, for many states, the pure state entanglement using this geometric measure is easy, relatively easy to calculate, sometimes analytically, and therefore you can get a lower bound. And for certain states, it's even better that they are actually the same. Okay, but the left-hand side to calculate generally is very difficult. Okay, so let me give example of this geometric measure of entanglement. Suppose I have a two-qubit state like that. I know the concurrence is really 2 times the AD minus BC. So AD is this combination. So that's concurrence. So, but what you could also ask, what is, in terms of picture, this is psi, and what is the closest state to that, the closest product state? And so it's sort of easy to see that the product state need to be of this form, right? This product 1, and I can just use another C2, 0, 1, okay. But since this state is symmetric under permutation, so I can use symmetry to simplify the calculation and just assume this is the same for the product state. Right, and this can be proved that you can simplify if the original state is permutation symmetric. Okay, so I'm going to have a product state, and I want to maximize this. I want to maximize this over the parameter C. C is from 0 to 1. Okay, so I don't put I should put absolute value, but they are real and positive, so I don't need to do that. But you can see that the contribution would only come from 0, 0, and 1, 1. So the only place it has 0, 0 is this combination that has coefficient c, right? Square root c times square root c, and the coefficient of p, square root p. And the 1, 1 would have the coefficient 1 minus c, right? So that's the, and I want to maximize, I forgot, I need to write maximize over c, right? Because this is a linear combination in a segment. So depending on which one is bigger, it could be like that. The maximum point would be at one end. It's either c equal to 0 or c equal to 1. So this means it's the maximum overlap is basically, I think this is extra. It's basically either square root of p or square root of 1 minus p. Yeah, in this case, if it's square root of p, the product state that's closest is 1 is 0, 0. In this case, it's 1, 1. Okay, there should not be a coefficient there. Okay. So in some sense, for the concurrence, it looks like that. For this maximal, I think it's something like that. Okay, square root. There's some curve, but yeah. Okay. But then, what about more complicated case? So GAG state is similar to this, the first example with p equal to 1/2. So you can see the maximum overlap is 1 over square root 2. So in some sense, that's the cosine angle. Right? Cosine. The angle is pi over 4. Okay. And what about the W state? This, in order to compute this, we need to write down the product state, right? So, and it's also permutation symmetric. So I'm going to write this 3 times, right? And the only place I want to identify the contribution will only come from when I expand this. I would have combination of 0, 0, 1 and 1, 0, 1, 0, 1, 0, 0. So that involving 0 twice and 1 only once, right? So if you expand, the only contribution that you will see is this. When you expand, okay? So the overlap W state with this product state is basically 1 over square root 3 c times 1 square root 1 minus c. Okay, then you maximize and you see that this is 2/3. Okay, so I have a plot here. I think I'm missing a 3 because this overlap with this each contribute to 1. So I have 3 copies of that. So that should be a 3, and this is the expression. This is function of c. You can see the maximum is here. Okay. So basically, this means the closest product state. I mean, you naively would think it's 0, 0, 1, any of the 3, but it's not. It's actually when c is square root of 2/3. This product 3 times is the closest. Okay. You could also, yeah, any question on this? This is really just algebraic. Okay, and you could also consider a more general permutation symmetric state. If a pure state is not permutation symmetric, then you cannot assume the closest product state is this. But you only have basically two n parameters, and you can numerically optimize that. I don't see an app for that. You'll need to download one. Somehow my Siri is speaking, responding to my quantum information class. Okay, so, but I want to mention interestingly that for these symmetric state, these permutation symmetric state, we have derivative entropy of entanglement exactly this. So for example, for the W state, it's 1.168 roughly. And for GZ state is 1. So in this sense, the W state has a larger, higher entanglement. Yeah. So there's also the issue of how do I compare which one is higher, which one's lower, because in other contexts, using other measure, it may happen that the entanglement of GSZ may be greater. Okay, for example, if we treat that as a bipartite system, I may partition 0, so 1, 2 versus 3, then in terms of bipartite state, the GSZ state may have higher entanglement. Okay, so really the order, it depends on how you quantify. Okay, any question? I think I have a few more minutes, but I just want to mention, last time we talked about one-way quantum computer, and this geometric measure of entanglement actually is useful in some way to characterize whether a state is useful or not. But it turns out that using this entanglement measure, it was found that if you have too much entanglement, the state would not be useful for one-way quantum computer. Okay, so too much entanglement is useless. Of course, too little. I should also stress that too little. So, but the exact definition of the entanglement is using the geometric entanglement. And they show that if the entanglement is n-qubit entanglement is greater than n minus just a constant delta, then that's what they mean by too much entanglement. Okay. So there's also similar result from other group, but I like the quote by Dave Bacon. He says entanglement, like most good things in life, must be consumed in moderation. So, and also is for quantum computation. Okay. So I think I want to skip this because this is, but maybe that just mention the construction, the definition to mixed state is also using this convex Hall, just like the entanglement formation. Okay. But that complicate the calculation. Of course, for certain symmetric case, we can have analytic results. Okay, so I want to pause here to see if you have question. Okay, no question, but let me preview what I'm going to talk about. next week. So there is one thing that was missing that I did not explain, is when I mentioned the dilution, I sort of use this idea of quantum data compression. So I want to close that that missing part, but and hope to be able to complete this picture, right? So we mentioned this dilution process. So the way to do that is you sort of prepare that locally. You prepare n pair of lower entangled states, and what you do is you compress the blue qubit into a smaller one, and that smaller one is k. It's actually n times the entropy, entanglement entropy. And so what you do is you compress the blue one and you use k copies of Bell state. You can teleport the blue qubits to Bob and Bob decompress. So if you can understand this process, then you understand the entanglement cost, right? So that's something that I hope, I was hoping that I could explain that today, but we're running out of time. But hopefully next time I will be able to explain this quantum data compression, and you will be able to understand this, finally understand the full picture. Okay. Yeah. Any more questions? I saw there's a chat. Okay, there's okay, that's from Yushen about quantum computing challenges. Feel free to look at that and maybe participate. But if there's no further question, I would end the lecture here and see you next Monday. And just remind you that the homework is due. Okay.
On Sunday.
Yeah, on Sunday.
Okay. Thanks.
Okay. Thank you. I'll stop recording.